In this example, we are given a system that produces the output y0n when the input is x0n. The problem asks us to determine the response of the same system to a new input, x1n. In the other words, we need to find y1n. Let's see how we can solve this problem. As a first step, I redraw y0n in a slightly different form. Notice that the sequence has a value of 1 at n equals 0 and the value of -1 at n equals 0, while the value at n equals 0 is still 0. Why do we rewrite the signal this way? Because if we compare this expression with x0n, we can see that the first part is simply x0 and shifted 1 sample to the right. In other words, it is x0 and -1. Similarly, the second part is x0 and shifted 1 sample to the left and multiplied by -1. Therefore, it can be written as -x0 and +1. As a result, we can express y0n as x0 and -1 minus x0 and +1. Now let's recall an important convolution property. The convolution of any signal with a unit impulse is equal to the signal itself. Also, the convolution of any signal with a shifted unit impulse gives the same signal shifted by the same amount. Using these properties, we can rewrite the previous expression. The first term becomes the convolution of x0n with delta n -1. The second term becomes the convolution of x0n with delta n +1 multiplied by -1. Now we can factor out x0n. This leaves us with delta n -1 minus delta n +1. On the other hand, we know that for an LTI system, the output is equal to the convolution of the input with the impulse response. Comparing the two expressions, we immediately conclude that the impulse response is delta n -1 minus delta n +1. Now that we have obtained the impulse response, finding the new output is straightforward. The output y1n is equal to the convolution of x1n with hn. Substituting the impulse response, we obtain x1n convolved with delta n -1 minus x1n convolved with delta n +1. Applying the shifting property once again, this simplifies to x1 n -1 minus x1 n +1. Now all we have to do is construct these two shifted versions of x1n and combine them. First, let's form x1 n minus 1. This is simply x1n shifted one sample to the right. Next, we construct negative x1 n plus 1. This corresponds to shifting x1n one sample to the left and multiplying all amplitudes by negative 1. Finally, we add the two sequences sample by sample. At n equals 0, the output is negative 1. At n equals 1, the output is negative 2. At n equals 2, we have 1 and negative 3, giving negative 2. At n equals 3, we have 2 and negative 4, which again gives negative 2. At n equals 4, the positive and negative values cancel, so the output is 0. At n equals 5, the result is 2. At n equals 6, the result is also 2. At n equals 7, the output is 2. Finally, at n equals 8, the output is 1. This is the final output sequence y1n. This example demonstrates how convolution properties and impulse response can be used to determine the output of an LTI discrete time system without performing direct convolution. If you found this tutorial helpful, please like the video, subscribe to the channel, and stay tuned for more signals and system solved examples.